Good day, everyone. I am Fianale Patrice Garcia, and together with my groupmate, Mr. JC Ferry and Mr. Mark Angelo Trinidad, we're going to discuss about the earth fault protection functions for long cable feeders in a compensated network. So, in this topic, a compensated medium voltage cable network. So this network is compensated using inductances and earthing resistance in a parallel connection. So this lesson will focus to the earth faults occurring in a feeder with the length up to a 65 kilometers. So first, let's go here in the network fault situations. Ayan. So the network fault situations. So there are two types of fault in the network. First, we have the symmetrical faults. So these faults are easy to calculate because network can be translated to a simple single-phase equivalent circuit. So symmetrical fault is a three-phase short circuit and secondly, we have a asymmetrical fault. So these faults are more common than symmetrical faults. So the most common fault causing is asymmetrical is an earth fault. So when faults are asymmetrical, network can no longer be transformed to a single-phase equivalent circuit and the whole network has to be treated as a three-phase circuit in its original form. So first is let's tackle about the first types of fault, which is the symmetrical fault. So what is a symmetrical fault? So symmetrical fault is a very rare situation. And as mentioned before, it is a three-phase short circuit is a symmetrical fault. So although this type of fault is very rare, it has to be taken care of because it is the most severe accident that the power delivery system will face. So one of the common three-phase short circuit is generator fault. And the fatality is caused by a very big fault current. So this very big fault current is produced because it limits the inductances are very small. And the fault starts from the subtransient current, which lead to the steady state full current values. So fault detection and clearing has to be very fast in order to limit disturbances to the power system. So that is the first type of fault, which is the symmetrical fault. So moving on to the second one is we have the asymmetrical faults. So asymmetrical faults and the asymmetrical faults more often occurring fault is asymmetrical fault. When fault is asymmetrical, fault currents and voltages are not equal at different phases. So there are two main types of asymmetrical faults, which is the shunt type and the series type faults. So the first one is the shunt type. So shunt type fault is a connection between the two network elements. And the series type means broken connection at the end of the conductor. And the most common asymmetrical fault is an earth fault. Asymmetrical fault indicates itself easily and from the phase values, it is easy to acquire what type of asymmetrical fault it is. And the studies of the network's asymmetrical faults are important because of the network protection. And studies are usually carried out by the method of the symmetrical components. So moving on to our basic theory and data of the earth faults. So basic theory and data of the Earth fault. So the Earth fault is a situation where a non-earthed live part of the network is connected to the Earth through relatively low impedance. So it can be a permanent fault which requires the personnel to rectify the fault situation. Or it can be a transient fault, which can be managed via automatically controlled protection system. And the critical use at the earth fault is the magnitude of a fault resistance. And if the magnitude is relatively high, electricity supply can be continued even if the fault is permanent. So four basic types can classify earth fault type. So these types are shown in the figure. The simplest type is a single phase to earth fault as shown in the point 1. So this is the single earth fault. So this is the figure of it. So that first figure is the most commonly caused by a wire drop. Second alternative is a two-phase earth short circuit as shown in the point 2. So this is the figure 2 which shows the two-phase earth short circuit. And that type of fault, two different phases are short-circuited together with the earth. And the third alternative is a double earth fault, where the two different phases are simultaneously connected to the earth at the different locations. So this is the figure of a double earth fault. And this alternative is shown in the point 3. So that the next one is the fourth fault, which is a cut wire where the load side is connected to the earth as shown in the point 4. So sabi dito, load side is connected to the earth. So this is the fourth figure, which cut the wire and fault on the load side.
So, basic theory and data of earth fault. Most common reason to earth fault are, for example, arc dueling lightning and trees which have fallen to conductor and animals. So, which are moving near living wire. Live wire is usually that during the earth fault, there are also some other faults. In some cases, earth faults maybe lead up to more complex situation like two-phase earth fault. Although the number of earth fault is large, they are usually temporary. Today's relay technology has also improved the situation, and harmful effects of the earth fault can be measured by two alternative ways. First of all, you have to measure whether the fault is fatal to human beings. Second, you have to measure how harmful the fault is to the property. And it is estimated that 80 to 90% of the faults in the main network are earth faults. In some cases, earth faults may lead up to more complex situation, like two-phase earth fault. Although the number of earth faults is large, they are usually temporary. Today's relay technology has also improved the situation. When modern protection relays have artificial intelligence, they normally are able to reclose network after the arc is cleared. So next, basic measurement at fault situation. So basic measurements during the faults are carried out with voltage or current transformer. Also, combination is possible. Transformers are used because the value are too high to be measured directly. So, both magnitude and angle values are needed. Measured value are normally compared to known healthy state values. If any changes occur, needed operation are carried out. And an earth fault situation at the compensated network is always challenging for feeder protection. When determining value for protection, many variables have to be known: length of cable and types of cable are some issues to be mentioned. In the earth fault calculation, the network is simplified to a partial network, which contain only crucial components. This makes calculation and logical deduction much easier. So, earth fault protection. So, the earth fault protection is under by microprocessor based relay. So, next, earth fault in the compensated network. So, the protection of distribution network is a complex issue. Key solution for the challenging procedure today is a microprocessor-based relay. It can protect sensible parts of the network with good accuracy. So, this is possible relay ability to monitor massive amount of network value. Before, it was common the one relay measured only one value. Revolution happened when mechanical relays were replaced by microprocessor-based unit. So the value which can be processed through modern relay can include, for example, the current, voltage, frequency, and power. From these values, it is possible to measure the differential between measured value, a symmetry, or between different phase angles, and even determine the fault location. Normal setting value include, for example, the trippings delay. And although the accuracy is the best characteristic of a microprocessor-based relay, nearly as beneficial feature is data recorded. It makes possible to view fault situation after the fault and monitor what's really happened. Next, the operational characteristic. So, protection method which are in use in this thesis have each their unique operational characteristic. They are applied to directional earth fault protection is compensated networks, which is the main topic of this thesis. Our operation characteristic define the borders B40 between the operational and the non-operational areas. Usually, the marked areas is the operational areas. But in the case of admittance characteristic, it defines the non-operational areas. In case of residual current-based earth fault protection function, the operation characteristic is drawn such that the vertical axis is taken as reference and it represents the phase angle of polarizing quantity. Typically, the quantity is the residual voltage of UO. Normally, the characteristic is drawn so that the UO vector is taken as reference. So, the left-hand side of operation characteristic indicates capacitive current and the right-hand side inductive current. So, when the measured value moves from non-operational area to operational area, desired operation would be carried out. Example of this operational characteristic is shown in the figure 19. So, this is the earth fault in the commutative network. So, In this figure, the operational characteristic with vectors of IO and UO. Operational area is colored with white and the non-operational area is with red. So, next tayo. Elements of the protection system. Elements of the protection system. The network is built from different elements which all have different tasks. Those elements can be divided to power carrying, measured, and protecting elements. Power carrying elements are transmission lines, transformer, generators, and loads. Measuring elements are instrument, transformer, and sensor. This sensor provide information to protection elements. So protection relays and switches are protected elements. So these elements from the main network which is measured and studied in this thesis. At case of this thesis, measurements for the protection elements are carried out at the beginning of the studied feeder. The needed values vary depending on the protection methods, but the overall current and voltage from each phase are needed. For each fault protection, zero sequence current IO and UO zero sequence voltage measurement are enough. However, also phase angle between IO and UO is relevant information. When angle information is used to protect, the method is called directional protection. This thesis concentrates on 4 different protection which are all directional.
Okay, so next is the elements of the protection system. So elements of the protection system. This is the network built from different elements which all have different tasks. Those elements can be divided to power carrying, measuring, and protecting elements. So the elements of the protection system, it can be divided into 3. So una is yung power carrying, which is yung elements such as transmission lines, transformers, generators, and loads. The next naman is yung measuring elements, which is yung mga instrument na kagaya ng transformers and sensors. So sa transformers, meron tayong tinatawag na power transformers o PT, and then yung current transformers o CT. Then sa sensors naman, this provides information to the protection elements. So example ng mga sensors na to is yung protection relays, switches, overloads, and etc. So these are the protection elements. These elements form the main network which is measured and studied. So the case of these measurements for the protection elements are carried out at the beginning of the studied feeder. The needed values vary depending on the protection methods, but the overall currents and voltages from each phase are needed. For Earth fault protection zero sequence, current IO and V data, zero sequence voltage measurements are enough. However, also phase angle between I theta and V theta is relevant information. When angle information is used, protection method is called directional protection. This thesis concentrates on the different protection methods which all are directional. Next is the instrument, transformers, and sensors. So instruments, transformers are special voltage and currents transformers. So kagaya na sabi kanina, meron tayong power transformer o tinatawag din na voltage transformer. And then yung current transformer natin, which are built to measure values from the electrical network. So ito yung kadalasan na, ito yung ginagamit pang measure nung value nung voltage and current dun sa ating electrical network. So when using instrument transformers, it is possible to protect sensitive protection relays of dangers of primary system. So kaya ginagamit yung PT and CT pang-measure nung um, voltage and current dun sa ating network is for the protection of ng mga equipment natin na nakakonect dun sa may protection, sa may power system natin. These dangers includes, for example, network overvoltage, galvanical separation of measurement circuit from the primary system is also benefit. An instrument transformer also allows setting up measuring equipment far away from the measuring point itself. Standardization of monitored values is also an important issue when measurements are carried out. Current transformers' secondary winding load resistance should be held near zero and voltage transformers' secondary winding load resistance should be held near infinite. All instrument transformers are graded by their transformation of accuracy. Next, earth fault current compensation equipment. Fault current in unearthed network is always reactive because of overhead lines and cables earth capacitance. So according to the law of determining capacitance of capacitor, earth capacitance is always bigger when cable network is introduced. So kaya tayo gumagamit ng earth faulting dun sa ating power system is to increase yung capacitance ng earth. Kaya nag-introduce tayo ng bagong cable network dun sa ating power system connection. Current compensation equipment is a device which is connected to the neutral point of the high voltage to middle voltage transformer stations and beside. It can also be called Peterson coil by the name of its inventor. The basic principle is to add inductance in parallel with network's 45 degrees earth capacitance. Inductance can be fixed, controlled by certain steps, or continuously controllable by local or remote control. Normally, 80 to 120 degrees compensation level are used. But due to the specifications of protection procedure exact, 100% compensation level cannot be applied. A resistor can be also added into the parallel connection with the compensation coil to increase resistive fault current. This is carried out to ensure proper functioning of the directional protection. If resistive current is absent, directional protection won't work. Okay, so next is the protection methods. The protection methods are always based on one of our more values derived from the network. The final value can be reached via simple calculations. However, all methods used in this thesis have V data as a trigger. Fault is detected only after V data has risen above its setting value. So protection methods is reached through simple calculations, which can detect fault only after the conditions or the setting value is reached. So when traditional protection methods are designed, due to limited calculations, power of protection relays, they are designed to be simple. The simpler the calculation algorithm is, the faster it is. The less clock cycle is needed. The more reliable the protection method usually is. During today's era of powerful microprocessors, this is a minor problem. In this, when attention is paid to protection methods which are proven to be good for normal earth fault protection procedures. Novel protections methods called admittance protection method is also used. All these protection methods are described in the following slides. The next is base angle criterion. Base angle criterion measures zero sequence voltage or V theta and zero sequence current or I theta. Vectors V theta and I theta have their maximum magnitude setting values. If these values are exceeded, the start operation will be carried out. The angle theta between zero sequence current and voltage is also direct. Normally, the operation sector is positive or negative 80 degrees or 160 degrees. So if the middle point of the operation sector is negative 90 degrees, the area where angle theta can travel is from negative 170 to negative 10 degrees. Note that it is essential to remember that in this protection procedure, both magnitude and angle values are used. So kadalasan dito sa may ganitong protection procedure, yung magnitude and yung angle is kadalasan ginagamit. The magnitude the magnitude or the angle cannot alone cause protection relay tripping. Next, I theta cosine protection method. The I theta cosine express networks resistive current. So dito sa may method na to, ito yung nag-express nung resistive current dun sa ating network. This method is widely used in compensated networks. In the compensated network, which is driven with 100% compensation degree, the fault current consists mainly of resistive current. The amount of reactive current depends on the compensation degree. When the amount of the resistive current increases, the phase angle moves to the direction of the resistive current. The direction where the angle that goes depends on whether the network is driven under or overcompensated. When the current has been increased enough, the angle moves to operational area and desired operations are carried out. Next, wattmeter protection method. A basic principle of watt metric is to measure zero sequence values active power. It's I theta cosine value multiplied with magnitude of zero sequence voltage V theta. The sign plus or minus tells if the fault is at protective feeder or not. So dito sa may watt metric protection method. So para ma-determine yung protected feeder kung may fault siya, ginagamit yung sign na plus or minus. Although watt metric is an old protection method, it is still a powerful way to detect low resistance earth faults. The negative aspect of this protection method is that it cannot detect high resistance earth faults if the parallel resistors of the Peterson coil is not used. When watt metric method is used, measurement accuracy is really important. When the measured values are small, even a small error causes a big difference in the final values. To make values more readable, usually applicable resistance is connected in parallel with the compensation coil. Proper fitting is necessary because if the resistance is too small, the neutral point voltage magnitude shrinks too much, and if it's too big, it renders useless. Okay, so next is the neutral admittance protection method. So in this method, it is based on zero sequence voltage V theta and zero sequence current I theta. So with the law of Ohm's or Ohm's law, admittance is reached by dividing current vector by voltage vector. The result of this division is also vector, and normally this vector is placed in admittance plane, where horizontal axis shows conductance and vertical axis shows susceptance. So when using this method of protection, it is suggested that the parallel resistance of Peterson coil is permanently connected. Even though this protection method is rather new, it is already widely used in Poland and other countries. Okay, so for our conclusion, from the protection points of view, all simulations gave promising results. On the one hand, long-studied feeder length doesn't cause harm when the simulated protection methods are used, but on the other hand, there is no decent solution to lower the resistive current at the actual fault location. No attention was paid to find a solution for that problem because main focus was to test the traditional protection methods of their performance. During the simulations, all these functions showed rather good performance in the ranking. The best method was the neutral admittance protection method. Then what metric is the next? I cosine theta and base angle criterion. Superiority of the admittance method is explained by a systematical way to identify Earth's fault and flexibility for different feeders lengths. As a next the result, finding of nonlinear behavior of the result fault current when the studied feeder length increases to nu never before tested levels. So that is all for our report for today, and thank you for listening.